We got 3 more examples in this video, different kinds of examples. So every one is showing something different concepts, different things that can pop up that you will see. Okay, so what we're going to start with is example 3. If R is the region between graphs of f of x and g of x, I should tell you what those are. F of x, that's going to be sine of x, and g of x is going to be cosine of x. Over 0 to pi, the answer is find the area of R. So let's visualize this. And let's not visualize it on Desmos. Let's remember our trig. What does sine look like? Well, sine is a wave like this. Has period of 2 pi, so this is 2 pi. Well, here we're only looking from 0 to pi. Remember that's pi, so we can actually get rid of all this other region over here. Not important. 0 to pi. And cosine is very similar to sine, right? It just starts at its peak. And when sine is at its peak, cosine is down here. And then it goes down there as well. So that's what cosine looks like here. And we're saying that R is the region between these two graphs. So that's going to be this region. And that's going to be this region. And we're going to have to add these two things together. We have a composite region. We need to know where this is. Because F, I should have colored it better. So I will. Let's say F is green, that's sine. It looks like this. And let's say G is yellow. Well, yellow's on top and then green's on top. We have to find where to split up the two integrals to get the red and the blue regions. So they intersect when sine of x is equal to cosine of x, just like we did before. Where do they intersect? Where is sine equal to cosine? And there's a couple of ways of evaluating this. I think the easiest one is just if you think about what sine and cosine are. On the unit circle, sine of any angle is going to be the y-coordinate on the unit circle. And cosine of any angle is going to be the x-coordinate on a unit circle. So sine and cosine are the same when the x-coordinate on a unit circle is the same as the y-coordinate on the unit circle, which is at an angle of pi over 4. And then graphically, that does make sense as well. This is pi over 2 right here. And if I drew my graph more pretty, then it would correctly look like symmetry. So they intersect at x equals pi over 4. Now we just set up two integrals. We have the red integral from 0 to pi over 4 of yellow minus green. And then we're also adding the blue area, which is the integral from pi over 4 up to pi of green minus yellow. Evaluate those integrals, add them together, you've got your answer. And again, that's if you want to use some other methods, there are some other things that you can say for some shortcuts. Like this, to the left of this white line, that blue area is going to be the same as the red area. So you could actually just find that red area twice. And then similarly, this white area is the same as this white area. So you could actually just find one of these twice. There's shortcuts you can take if you know what this graph looks like. But I'm expecting you to just evaluate it directly. So again, once you get here, it's all just chapter 1 stuff. which is why it's important to be good on chapter 1. I'm not going to take the rest of the video to do it. I'll give you the answer as an approximation, but you should be able to do this by hand. It would be good practice, but at this point, we have done enough of these. I do not feel like we need to do another one. I don't need to just fill video time is my logic here. So what it should look like is just the integral from 0 to pi over 4 of cosine minus sine plus the integral from pi over 4 pi of sine of x minus cosine of x. So your final answer should have pi's in it, or square roots probably, not pi's, probably square roots. But the decimal approximation should be about 2.8284. But I will want the answer with the square roots and stuff. I'm just not going to take the time to do it right now because I want to do more examples. And I want to focus on the new stuff rather than the old stuff. So let's look at example 4. Oh, I was looking at the wrong video notes for a second. Let's do example 4. All right. Find the area of R. And then this one actually give you a little picture. So here's our graph, and then we have one curve, which is just a quadratic. This is going to be f of x equals x squared. And the other one is going to be a line. It's going to be g of x equals 2 minus x. And I'm asking about the area under the curve. This green area. So this doesn't immediately look like a composite region, right? It's just one region. But we have to think about how we're going to compute it. Well, the blue curve is not involved at all to the left of this. And the red curve is not involved at all to the right of this. And in fact, this really does become two areas. Green and yellow are way too similar, right? It's two regions. The area of this white triangle and the area of this green shape. So we still have to split it up into two integrals. Or again, you can use your donkey method to find the integral, the area of that triangle. Yeah, let's do. Yeah. So technically, right, what we have, we need to know where they intersect. Right? So they intersect when x squared is equal to 2 minus x. That's a quadratic. X squared plus x minus 2 equals 0. X plus 2, x minus 1. So they intersect at x equals 1, and then also negative 2, right? Some point up here. So they intersect at this point right here, which is at 1, comma 1. You don't really need the y coordinate yet. A little foreshadowing, a little spooky music. Playing Darth Vader's theme when Anakin's on the screen. A little foreshadowing. We don't need the y value yet. I guess it's not that much foreshadowing. You can literally see the title of the videos. The next one is called something like regions with respect to y. Has y in the name. Okay, and then yeah, we have two integrals. Integral from 0 to 1 of just the red function plus the integral from 1 to 2 of the blue function. And again, the second one is just a triangle. All right, it's just a triangle of base 1 from 1 to 2 and height 1 because we found the height. So we know this guy is actually just 1/2 base times height. This integral is just 1/2. The other one we'll have to do more directly. We can do that really quickly on the next page. Should not take too long. X squared So, oops, that's a 2. This definite integral for x squared is just 1/3 x cubed from 0 to 1, which is 1/3. So our total area is just 1/3 plus a half, which should be 5/6. But again, the point of this example is to show that even though it may not look like a compound region, we still have to split it up into 2 integrals. Always look at the region and try to see and remember area under a curve is integral. So how are we calculating these areas? Technically, it's the net signed area for integrals. And that's useful as well. Okay, let's do the last problem for this video. And this is actually an application problem because a lot of people might be wondering, where is an application for areas between curves? Okay, wait, I thought it was 45. No, it's 49. And the short answer is there kind of isn't. Because all this section is, right, is the area between 2 curves. But look at what we're doing, really. Let's go back to this example of just and we'll use 5 minus x squared. And just let's use the one with x being equal to 1. So the area between these 2 curves is really just the same as the area under a single curve. We call h is just, right, hold on, f of x, this is g of x. Well, if h is just f minus g, the area between white and blue is the same as the area under orange. So really, you can just go back to chapter 1. It's the area under a single curve. And every single one of these examples can just be modified in this fashion by taking the difference. Area between white and blue is the same as the area under orange. All right. Now, so sometimes this making of the orange function simplifies things and makes a lot of sense. And sometimes making of this orange function doesn't really simplify things. And it's easier to think about things in pieces. So for example, in this homework problem, number 49, we're looking at profit. Oh, I spoiled it. Crap. We're looking at cost and revenue, which has something to do with profit, maybe. And cost and revenue are 2 different functions. Think of the cost and revenue as the white and the blue. So if revenue is higher than cost, that's good. Profit will be the difference. Okay. And remember that area is the same. We can think of area as net change. If these are derivatives, then the net change of the original quantity is just the area under the derivative. All right, if these are velocities, then net change of position, otherwise known as displacement, is that area. If these are rates of change of population, then the total amount of population change is that area. So similarly, if we're looking at just the area between white and blue, that's going to be, if these are derivatives, the net change of that original quantity that we care about. All right. So if we look at Hoover Dam again, we don't need you anymore. Sorry, Hoover. Look at 49. So we have a factory here, and that's selling cell phones, and it has a marginal cost function. Again, a lot of times with business and economics applications, the word marginal is a good indicator that you should be thinking of derivatives. Marginal cost is basically the derivative of the cost function. Another way to think about marginal cost is at a certain production level, X. So look at this cost function. As a certain production level X, this marginal cost function tells you how much is it going to cost us to produce the next unit. Because, and that's going to change. If you're at a good optimal level of production, then the cost of increase of creating one additional unit is probably not going to be that much more. But if you're making way too many or way too few, then that cost of an additional unit is actually going to be much higher. Okay. And then marginal revenue is the same idea. At any production level R, this marginal revenue function tells us, well, how much revenue are we going to get? How much more revenue are we going to get if we add one more unit? And then that also leads to marginal profit, which is the difference between these two, because profit is just revenue minus the cost. So we got a marginal cost function and a marginal revenue function, and we want the area between these two curves. You don't have to graph this one by hand. I've seen some math classes in older times mostly where you have to graph cubics. Oh, these aren't cubics. Oh, you could graph these by hand. It wouldn't be that bad. Just a little annoying, but not that bad. All right, so our cost function, marginal cost function, C of X is 0.01 X squared minus 3X plus 229. And the marginal revenue function is 429 minus 2X. Again, these are derivatives. This is the derivative of the cost function. This is the derivative of the revenue function. So area under the cost function is going to be total cost. Area under the revenue is going to be total revenue. And now let's graph these. So let's get some things that, a scale that makes sense. And we're going to look from, I don't know, maybe 0 to 100 or something. I don't know. Oh, not 0 to 100. Sorry, I was trying to change the X's. All right, maybe 200 is more important. Oh, if we go to 300, maybe we see, or 250 or something. Oh, what? Now I'm blocking the way. All right, let's go to 300 so y'all can see. Or then, you know, I can always do this thing where if I'm really talking about important stuff and we need a lot of board space, then there's a way around that too. Here. Fixed. Now you can see the whole graph. Okay, so we'll have ghost Jason for the rest of this video. So the top here, also let me make this more visible to you so you can actually see the color coding. The top is a revenue function. Great. Revenue, marginal revenue is higher than marginal cost most of the time. But eventually, at a production level of 200 units, now the marginal revenue is not very much compared to the marginal cost. So at 200 units, the marginal revenue and the marginal cost are the same thing, which means that the revenue from an additional unit and the cost from an additional unit are the same. So you would naturally think, why make any more? There's supply and demand and price functions, but in general, it doesn't make sense to make more if, and it certainly doesn't make more after 200 units. Okay, let's actually talk about the problem because I'm just talking about marginal cost and marginal revenue right now. So it has this marginal cost function. X is just the number of cell phones being produced. So we found out that at 200 cell phones being produced, something's happening. And a marginal revenue given by that. Find the area between these two curves and X equals 0. Find the area between these the graphs of these curves and X equals 0. So it doesn't want the area between the two curves here. It wants the area underneath each curve individually, I believe. Oh no, X equals 0 is a vertical line. So it does want this area. The area bounded above by X equals 200, because that's their intersection, and bounded below by X equals 0, because that's when, you know, things don't really matter that much. We're not going to be doing negative production levels. So what we're going to have here is the integral from 0 to 1, from 0 to 200 of the upper function minus the lower function with respect to x. Again, this difference between marginal revenue and marginal cost is marginal profit. Profit is revenue minus cost, right? And in fact, if we wanted to, we could make the marginal profit function, right? It's just revenue minus cost. So the area between these two curves is the same as the area under the white curve. So the area between these two curves is the same as the area under, I just said that. And so remember, area under a curve is net change. What's the net change? If this is marginal profit, the antiderivative of marginal profit is going to be total profit. So that's one application here. It varies between curves. This is going to give us the total profit, which is about $33,000. All right. Total profit from producing 200 units, 200 cell phones. So again, you could do this by hand. It's just the power rule of R of X minus C of X. Again, these are marginal revenue and marginal cost. It's going to be 33,333.33, repeating. I'm going to say total profit from production of 200 cell phones is about $33,000, $333.33. Oh, right there, just like I was writing. I was transparent, but my internet browser was not transparent. There we go. It's a cool application of this. And again, this is really just the marginal profit, P of X. There we go. Let me know if you have any questions, and have a good one.